Vikan Bharti with Abhilash Sarkar. In the last video, we have finished uh, describing describing the effect of motion on any fluid. The effect which I'm talking about is the pressure energy, how it is being deviated or how being affected with respect to the steady state conditions. Okay, now we'll learn some useful instrument which are always being used in our fluid statistics study. So the instruments are, the first one of the instrument that is very much useful, and it has some, not only instrument, it has been developed with some concepts. That concept later stage so many scientists has used to, you can say, to prove their theories or to establish new concepts on fluid statistics or dynamics, you can say. So the instrument I am talking about is barometer. So this is the instrument. The function of this instrument to measure atmospheric pressure. This is the instrument for first which is instrumentally, or you can say physically, that has shown how to measure the value of the atmospheric pressure. So what the scientist behind is Mr. Torri Selly. He is the scientist behind this invention. What he has does is a very simple kind of you can say the arrangement, but very effective one. So what he has done, he has taken a container which is filled with mercury. This is a purposefully taken this fluid or liquid, you can say mercury. It is not even comes under the fluid. Actually, mercury is all if you say in periodic table, it is treated as a metal, but is a liquid. It's always in natural temperature and pressure. It is in liquid state. That's why it is taken as a liquid, and he has filled a glass tube with this. This is around 800 mm of height he has taken. He has filled this with this same mercury. He has inverted it inside the mercury column. Okay. So what he has expected, there is always a atmospheric pressure is acting on any surface, and after he has inverted it, it has come down and settled down at height which is physically measured as 760 mm. So what he has assumed, whatever pressure there in this column, because the vacant space is almost, the pressure is zero, because this is filled with the vapor of Hg, mercury, which is, the pressure is almost treated as a zero. So whatever pressure is there in this water in liquid column, that is mercury column of 760 mm, the pressure exerted here and the pressure exerted here by this column has to be equal, otherwise the liquid here will lift up or it will come down. It is stable in this condition. That means whatever pressure created by this mercury column and the balancing force or the pressure due to the atmosphere is created on the mercury column will be same. Okay, otherwise this will not be in equilibrium. That is the first and foremost concept. And if it is same, so we can say the atmospheric pressure is equal to 760 millimeter of Hg. Okay, so this is practically he has shown, but condition is that this pressure is varying with height. Second, the atmospheric condition. That means if there is a physical there is a change in parameter, that means if atmosphere goes at high temperature and low temperature, because theoretically this is nothing, this is millimeter of Hg, that means it is existing what? Because pressure is nothing but H, rho and G. Rho can vary with temperature and H will vary due to this difference in elevation. So both these will affect this standard atmospheric pressure. So where he has found this 760 of millimeter of Hg? At mean sea level. So his experiment has done at mean sea level. In any other elevation, if he goes up on the mountain, he will get a lesser value, because with the elevation up, the value of pressure goes down. So the pressure varies with the and atmospheric and density may change. Even if it is a ideal fluid, density will change with the temperature. If it is incompressible oil, if it is non-viscous oil, but that effect of temperature will always be there even in the ideal fluid. So density may change if it is atmospheric condition. So his assumptions are based on this. Okay, and he has nullified this vapor, because anything cannot be in vacuum in a complete zero condition. There must be something or otherwise the pressure will not be balanced from outside. Okay, the glass tube can hold due to its rigidity up to some extent. After that it will break down. So there are pressure, but that is negligibly small, that he has assumed. And as it is stable, there is no effect of this pressure there. This is not fluctuating. So at that condition, 760 millimeter of water column is the standard pressure for atmosphere. And this we have already learned. What is the value of that? We have learned this 760 of millimeter of water column. Sorry, 8 millimeter of mercury column is nothing but 1 atmospheric pressure, and this is nothing but 1.01 into 10 to the power 5 Newton per meter square, or this is that much of Pascal, 1.01 into 10 to the power 5 Pascal. That we have learned already. Okay, or this is equal to 760 millimeter 760 torr, 760 torr. So that means 1 millimeter of this is torr is named after Torricelli. So this is 760. So 1 millimeter of Hg is equal to 1 torr that he has established. So this is the case barometer. Later, Mr. Pascal, who is another scientist, he has invented in 1700 you can say century, 17th century basically. So year I forgot exactly, 17th century you can say. He has invented, Mr. Torricelli has invented this. Then after Pascal has come after him, and he has used this concept to describe his theory. So that I will teach you later. But the second instrument that is used, that is manometer. Manometer is used to measure the pressure inside any fluid chamber. So the another instrument is manometer. This is basically in practical way used in different plants where the system pressure has to be calculated, or system pressure live can be seen with this instrument. This is manometer. The simple arrangement of this is nothing but as a vessel which is connected to a this kind of you can say arrangement U2. This end some it can be found in two way, either it is blank or other case it could be open. Both are possible. What is the difference is that this is gas inside that. So due to the gas pressure, initially this is filled with the mercury with the same elevation. So the elevation, let's say this is H first. Now the gas when it is poured with gas, this container, and is connected to this, the gas pressure will exert a pressure in this, and it will move this fluid column down, and due to that there is a movement here also. Okay, and there is that it is open, that means atmospheric pressure will act on this, but this side there is no atmospheric pressure, this is gas pressure. So gas pressure is nothing but on the other side, this is the, let's say, the height raised due to that. So H1, and the rho is the mercury rho of mercury, whatever liquid will take, but this case mostly mercury is very stable. It is not creating some some vibration, or we can say the stability may come very fast, and so once it is disturbed, on other liquids coming stability is taking too much time, and the surface, it is very much easy to read. This is having concave surface on the top, whereas other surface, due to the surface tension, because the mercury surface tension is very less, other fluid surface tension, so some of the liquid they stick to the tube, the glass tube will take, and there is a error may come always, but in this case that doesn't stick to the glass tube, and the surface remains very firm. So reading is very much easy to get the correct reading. So if it is H1 being raised, so H1 into rho into the G will be the pressure due to this column, and apart from atmospheric pressure. So atmospheric pressure we know from the initial barometer experiment. The gas pressure is nothing but H you can measure from scale. Rho know the 13.6 gram per centimeter cube is the and G you know 9.81 whatever. So these values are known. H can measure. So this you can get, and this is already known. So from that gas pressure can be measured. Now if it is closed, only effect that atmospheric pressure will not come there, and only the difference due to the column, and this part will not be there. This will be directly can be measured from this. So this is the two kind of, but why it is not taken blind? Because if there is some gases entrapped, will not get the exact pressure here, so there some error may come. Okay, so if it is negligibly small, that is okay, otherwise some error will come due to this entrapped gas here itself. So you can try at your laboratory both way. Okay, but this is the this is the procedure by which you can get the gas pressure. In any industry, you might get this kind of manometer installed in the system, and there is two column, and by seeing the difference in the liquid column, you will get what is the exact pressure in the system is flowing. So this is manometer done. Next will come the Pascal's law. So we are just few while back talking about the Pascal. So Pascal, he has he has established some law. The law is, if any any pressure is exerted into a fluid, into a fluid which has contained in whether it's a contained in a vessel. Yes, contained, the language is contained in a vessel. This word is okay, otherwise you can use the container also. Container means this has to be packed from every side. There is no chance of entering or leaving any liquid fluid out of it. So vessel, he has taken this word to describe his theory. So has contained in a vessel, then that pressure, this words may not be actually the same that he has taken, but the meaning out of it will be the same, that will reflect the same. So that pressure, what I said, in any, if any pressure in is exerted into a fluid which has contained in a vessel, then that pressure will transmit into that fluid without diminishing its value and without diminishing value and without diminishing its value and that fluid without diminishing and if any pressure is exerted into a fluid which has contained in a vessel, then that pressure will transmit into that fluid in all direction without diminishing and transmitting same value. Okay. Now let me read it out again. If any pressure is exerted into a fluid which has contained in a vessel, and I am talking about, let's say this is a vessel, or you can assume it is a balloon also. It is a vessel which is containing a fluid. Okay. Now I am exerting some pressure into it, so that pressure will whatever pressure, let's say I am this having already 4 bar of pressure, I am exerting another 2 bar of pressure. So then that 2 bar of pressure will insert or exert into the liquid without diminishing. That means 2 bar of pressure will not reduce, it will be added to 4 bar in equal way, and it will exert same pressure in all directions. That means in the system as a whole I will get 6 bar of pressure, and that 6 bar of pressure will exert every part inside that vessel. It will, wherever I will measure, I will get the same pressure. Now if it is possible to get such container, such vessel, okay, now I am drawing some vessel, you will understand what I am saying further. Let's say there is a vessel have different opening in different direction. Okay, now this is already having some liquid. As per him, if I put a pressure here, is already having a pressure P1, I am exerting another pressure P inside. So that pressure added with this P will exert, if I measure it in any other part. If this pressure is exerted inside this will not diminish the value, rather it will be added to the existing pressure and it will exert in every direction wherever you will measure. Let's say I am opening this, this will say this all pressure will be P plus P1, P plus P1, P plus P1, P plus P1. All this pressure will be same in every direction. Whatever direction you measure, you will get the same pressure. This is the Pascal law. Now if it is so that means there is an advantage of this theory, and if it is true, then there is an advantage of this theory. Now how that Pascal has come to that conclusion? First he has experiment the barometer. If he is telling the truth, so his that also stands good for Torricelli's theorem, because Torricelli has said in a container I am keeping an inverted tube and I can measure the atmospheric pressure. That means what theory is being used? I am putting a pressure and that pressure is equal to the to the column of that mercury, that is equivalent. So what he has done, he has taken this arrangement to different elevations and measure these values accordingly being varied. Okay, and wherever he has measured, Torricelli has measured, he has found that value is matching every time in that location, whereas when he is varying the location, the pressure is varying. That means there is, if it is a extra pressure due to the elevation advantage, that pressure is equally transmitted. That means to say, if for each height he is getting this much of additional pressure, so atmospheric pressure standard is now if you add directly, as per him this is the additional pressure and that has to be be in the system always. So when he has taken Torricelli's theorem, his result is matching with his concept. Okay, so he has used that theory to prove his own theory, and this theory, if it is true, then if this kind of arrangement can made, this kind of arrangement is made, will get some mechanical advantage out of it. How? Let's say there are two part of this arrangement and this is filled with incompressible fluid. Now if any force is exerted on that F1, and that pressure will that force will create a pressure inside this container, and that pressure will be transmitted to all direction, and the same way that pressure will be exerted on the piston. If I keep another piston here, this is a piston on which I am putting force F1, okay, and that is causing a pressure. That pressure energy will be without diminishing, it will move to all direction. One such direction it will move, and then it will hit on the lower surface of the piston. On the other arm, if it is so, then the force divided by the area, let's say this is area A1, this is area A2, and the force is created due to this force. So here, if I assume it is in equilibrium, after putting the force, that liquid column is come down and it will go up some height, and it will remain there. Okay, now what is the pressure energy here? F1 by A1. What is the pressure energy here? F2 by A2. Okay, now by seeing the diagram you automatically know A2 is much more than A1. Now if it is so, now if I take the comparison of the force that is there, the respective force will be the force in the same ratio that area is there. So F2 by F1 is A2 by A1. Now by seeing the diagram you know this is much more than 1, because A2 is much more than A1 I can see. So if it is so, then the force F2 much more than F1. So the F1 the force we have given, and F2 the force that is created. And what is the direction of F2? Upwards. What is the direction of F1? So downwards. So that means this is the effort I am giving, and this is the load I am lifting. So definitely if F2 is much more than 1, so that means what is this? Load by effort, which is the mechanical efficiency, and this case mechanical efficiency can be much more than 1. That means I have an advantage of using this theorem and can build a machine like this. Now you well understand this kind of machine we are using in practical sense in our garage. What is that? Hydraulic lift. Hydraulic lift, by which we can move a car of around 3 to 4 ton with a simple piston of dia not more than maybe 150 to 200 mm. So this is creating a pressure which can lift of much more weight of 3 to 4 ton of weight with a minimum pressure. This mechanical advantage is used there. So this has several examples there. So that Pascal's theory is used to build such mechanical arrangement, where the mechanical advantage is much more than the than 1. Okay. Now again I am just drawing this arrangement to establish some more relation of the case. This is the two piston, we can say. I am putting force F1, this is F2. Fine. So now this is incompressible fluid. So that means if a liquid column is coming down of height h1 here, and a liquid column at the same time it is moving height of h2 there, and cross section is a1, cross section is a2. So that means it is incompressible, that means whatever fluid will come down there, down, the same fluid will go down, because there is no additional fluid is coming. So whatever the whatever say or let's say the pressure we are saying F1 by A1 is equal to F2 by A2. And what is that here? It is equal to pressure 1 is equal to pressure 2 there. Now what is the pressure here? This pressure is equal to H1 and the liquid is rho and G. Okay. And there also H2 or else you can say not in this way, rather this is force cannot be same, so yes, that can be said as I can see that whatever liquid will flow from this side, that liquid has to be accommodated there, because there is no way out of taking out the liquid. So what is the amount of liquid is flowing from this side due to this force, because after it comes to the equilibrium, it will be like that. So what are the liquid it is flowing is A1 cross section into H1, means volume has to move the same A1 into H1. That means I mean to say whatever volume it is coming down here, the same volume has to be accommodated there. Okay. So if it is so, then the cross section into H1 is equal to the cross section A2 into H2, because volume whatever is displaced here has to be accommodated somewhere, because in between place there is no extra area or extra volume to capture up to this. Now whatever it is lifted up has to be displaced from here, it will accommodate the extra press due to this height. So that area into the displacement, and the area into displacement, volume flow rate will be same, because whatever volume displaced here has to be accommodated up somewhere. It will not get extra more extra due to any other reasons. So it has to be the same volume displacement here, it will be accommodated there. So that volume displaced here is the cross section into H1, that height displaced, and cross section into height displaced. So if it is so, then A1 by A2 is equal to H2 by H1. Now little while before, F1 by A1 we got F2 by A2. Now F1 by F2 we got A1 by A2. Fine. Now A1 by A2 is equal to F1 by F2. Now instead of taking cross section, because if I am not able to mention the get the cross section, by measuring the height also we can get what is the mechanical advantage with the height displacement, because displacement of height we can measure, there could be a marking from there, H1 and H2 can be measured. So F2 by F1 also can be represented with the height here in this case. Okay, because volume flow rate is same, because it is an incompressible fluid, so the volume flow rate would be same. Okay, so for ideal fluid volume flow rate is same. Why same? Because incompressible fluid does not compress, so that means density will not change. And what is your density? Mass by volume. Mass 1 by volume 1, mass 2 by volume 2, and mass is same so volume is same if density does not change. So volume is same, so cross section into height is same, cross section to height is same. From there we can establish the ratio of area in respect of height, and that too the force given and the force created or the load bear, the ratio I can get with the displacement of the piston or displacement of the fluid column. Understood? Here I will end my this session. In the next session I will move to the other subject of this fluid statistics. Okay. So thank you for now. Good night.